Hang on. Yeah, we were looking at stationary points, weren't we? What's a stationary point? What's a stationary point, somebody?
So it's 0, it means it doesn't move.
Yeah, exactly. So it's literally where the derivative is equal to 0. You happy with that? Why are we interested? I didn't really cover this last lesson, but why would we be interested in looking at stationary points? What kind of applications can you think of where stationary points would actually be quite useful?
When you try to figure out the maximum.
Yeah, exactly. So stationary points are trying to figure out like maximums or minimums, even points of inflection. Yeah, you remember points of inflection are this kind of thing. Yeah? So you can either have a maximum or minimums or points of inflection. But why is that useful? In the real world, why would finding maximum, minimums, things like that be useful?
Because that's the range of the data.
Okay, so an example, let's suppose I have a function which has time and amount of money, okay? So let's suppose I have a function which describes the amount of money that I'm expected to make through time, okay? Why would being able to find maximum or minimums be really useful there?
Then you know when you want to stop.
Absolutely right, yeah? If you're able to find the maximum or minimums of that function then you will know at what point in time have you made the maximum amount of money. Equally, you might want to buy stocks or shares when it's at a minimum, when it's at lowest. Yes, Odell?
So maybe for this function, maybe we can time as x and amount of money as y value,
Yes.
and dx over dy give us like the differentiation.
The rate of change, yeah, good.
The change, and then we can find the stationary values by like equating to 0,
Yes.
and then here
Yes.
time over amount of money, we can find it.
Exactly, but my point is the reason why we're interested in finding stationary points, it's not just for the fun of it, it's actually so that we can find when are we making the most money? Or when should we buy all our stocks and shares up because they're going to be the cheapest, yeah? So stationary points actually have a real life use, right? Now, we're going to move on to something slightly different today. We're going to move on to finding derivatives of trigonometric functions, okay? So slightly more complicated functions. If we have time, we're also going to move on to exponential and logarithm functions as well, okay? Yeah.
Can I ask on the forehand, do we have formulas for our last exam, or?
Yes, so that formula sheet which I gave you, that's what you get in the exam.
In paper-based exam too, right?
Yeah.
Oh, okay.
So all of your exams, you will have statistics tables and also those formula sheets as well.
I mean, because like there are tons of formula. I remember tons of formula because for the differentiation of trigonometric functions.
Okay, fine, yeah. It won't get that in depth with this, okay? But yeah, we are going to look at how to differentiate trigonometric functions. Okay. So could you, for me, plot this? Y equals sine x. What does that look like?
Like this.
Okay, so it's this kind of shape. Okay, let's plot a bit more. Let's plot a bit more on this. Okay. So this is x. This will have to be sine x. Okay, this is sine x. What's this point here? Y equals 0. What's my x value?
Pi.
It is pi. Good. What's this value over here?
2 pi.
2 pi. What's this value here?
3 pi.
Yeah, 3 pi over 2, 3 over 2 pi. What's this point here?
Pi over 2.
Good. Okay. Do people understand what I mean by this notation here? So this is an angle, okay, because I'm talking about sine of x. I'm talking about an angle. Do people understand what units I'm using here? I'm using radians, okay? Have people met radians before? So there's two types of angle measurements. There's degrees and there's radians. Now, in this course, we only work in radians, okay? We only work in radians. The reason being is because we're going to be doing calculus with trig functions. And if we have to work in degrees, it means we have to always multiply by a factor or divide by a factor of pi by 180. So if we work in radians, we don't have to have that horrible factor all the time. Okay? Now, do people know what radians are? What are radians? What are radians? What are degrees? What are degrees?
Degrees like the angles.
Okay.
Like 30 degrees, 40 degrees, or something.
Okay, good. So degrees are to do with angles. Okay, they're a unit of measurement for my angles. Okay. How many degrees are there in a full turn? How many degrees are there in a full turn?
I mean, 0 to 365, I guess.
360, not quite. Okay.
360, sorry.
So 360 degrees represents a full turn. Okay. But are you happy this is completely arbitrary? Okay. Just somebody's decided there's 360 degrees in a full turn, right? Now what that literally means, if you think about a full turn, okay, if you divide it up into 360 equal parts, okay, each one of those parts will be worth 1 degree. Does anybody know why they choose 360?
Some Greek guy did it.
It is actually, it is to do with the Greeks. First things first, how many days approximately does it take for the Earth to orbit the Sun? 365, exactly, which is about 360. About 360. So you're right with the Greeks, they try to embed as much of nature as possible into mathematics, and they realise, well, it takes about 360 days for the Earth to complete a full turn of the Sun, so why not just say that our angle of measurement, in other words, for us to complete a full turn, is about 360. So it is arbitrary. There is also another reason. It's divisible by loads of numbers. Okay, so is 1 a factor of 360? Yes, it goes into 360. Okay, is 2 a factor of 360? Is 3 a factor of 360? What about 4? 5?
Yes.
6? Yeah, 6 times 60 is 360. What about 7? 7 isn't, okay, but 8 is, and so is 9, and so is 10. So actually, if you have a look at the first 10 numbers, every single one of them is a factor apart from 7. Now, why is factors really important property if we're going to be dealing with angles? Well, I said that 1 full turn is 360 degrees. But if we want it to, so if we now deal with half a turn, are you happy that's still a nice number? Or a third of a turn is a really nice number. Or a quarter of a turn is a really nice number. Or a fifth of a turn, or a sixth of a turn, or an eighth of a turn, or a ninth of a turn, or a tenth of a turn. In other words, because we deal with like fractions of a turn, it still comes out as a nice number. Okay, if this is divisible by loads and loads of numbers. Okay, whereas if we use say 100, okay, fine, half a turn will still be nice, but a third of a turn will be horrible. Fifth of a turn will be okay. Sixth of a turn will be horrible. Eighth of a turn wouldn't be very nice. Ninth of a turn wouldn't be very nice. Okay, so we want to choose a number that's divisible by loads of numbers. Okay, however, because we're mathematicians, degrees are completely arbitrary. It's just somebody said 360 degrees. That's a full turn. Okay, there's no properties of a turn embedded in there. It's an arbitrary number which somebody's chosen. So if you have a look, this here is a circle. Okay, this is a circle. In other words, I want my angle measurement to include some properties of the circle. Okay, this is where radians come in. Okay, so what we say then is that if we look at the radius, okay, so remember the radius is the distance from the centre of the circle to the circumference, okay, and if we just sort of measure that distance, however long it is, and let's imagine taking a walk around the edge of the circle for the same length as this radius. Okay, so if this is my radius, I've basically gone for a walk around the edge of the circle for that same distance. Okay, now the angle which I've swept out through here, so the angle which I've moved through, is going to be 1 radian. Okay, so the angle which I've swept out when I walk around the edge of the circle for 1 radius is worth 1 radian. So my question is now, how many radians are there in a full turn? How many radians will there be in a full turn?
360.
No, that would be degrees. What I'm literally asking here is how many times does the radius fit in around the edge of the circle?
But isn't every degree, every is like 1 degree anyway?
Yeah, I'm not interested in degrees anymore. I've come up with a new angle measurement.
Oh, okay.
I want to include some properties of a circle in my angle measurement. So how many times does the radius fit in around the edge of the circle? It fits in 2 pi times. Yeah, it comes literally from my definition of pi. Remember, pi tells me how many times my diameter fits into the circumference of the circle. Okay, so my radius will fit in twice as many. So hence it's 2 pi. Yeah? So what I'm now saying is that 360 degrees is worth 2 pi. So now I can work backwards from this. So how many is 180 degrees going to be worth? It's going to be worth pi. If I wanted to do, say, 90 degrees, how many radians would that be?
Pi over 2.
Pi over 2. Okay, if I wanted 45 degrees, what would that be?
Pi over 4.
Pi over 4. If I wanted 10 degrees, what would that be?
Pi over 6.
Pi over 18. I've literally had to take this and divide it by 18.
Oh, sorry.
Yeah? What about 1 degree?
100.
Yeah, pi over 180. Yeah, does that make sense?
That's fair enough.
Okay. So basically on this side, I've got degrees, and this side, I've got radians. So if you've never met radians before, hopefully that is a bit of an introduction. By the way, if I wanted to go back the other way, and if I wanted 1 radian, how many degrees would that be? Start here. If I wanted 1 radian, what would I have to divide both sides of the equation by just to get 1 on this side? Over pi. Good. Okay. So hopefully that's a bit of an introduction to radians. I wasn't expecting to do that. Okay. So if you want to find out more about radians, then by all means go away and have a look. Okay. But effectively, if you just take away from this discussion that radians are just a new way of measuring angles, and we will always work with them in this course because we're going to be doing calculus with them, going to do differentiation, integration and stuff, then we don't have to worry about doing this factor anymore. Okay.
Does 1c represent radian?
Excellent question. Okay, excellent question. Didn't point this out. With degrees, the symbol for a degrees is like that little circle up there. Okay. For radians, the symbol is this little half a circle. The reason being is because pi, like our base unit, pi radians, is worth half a turn of the circle. Hence, we do this little half a turn of a circle up here. Now, just be aware, if we give our units, or if we give our angle in terms of pi, we assume it's radians. Okay, so you don't have to write it up here. But as soon as you start writing a number down, then you have to distinguish, is it radians or is it degrees? Does that make sense to everyone? Okay, good.